Hi, we're Team Awesome, and we're doing a presentation on VESPR Theory. I'm Kim.
I'm Haley.
I'm Paige.
I'm Rachel.
And I'm Caitlin.
So, this first slide is about discovering the VESPR Theory. The VESPR Theory is an extension of the Lewis model, and it shows the number of bonding and lone pairs of electrons that are present in a molecule. Based on the idea that electron groups repel one another, it hypothesizes the shape of each molecule. Some contributors to this theory are Neville Sedgwick, Herbert Powell, Ronald Gillespie, and Ronald Nyholm, and it was first used in 1940. The basic ideas of VESPR are that the structure of each molecule is determined by the interactions between the electron groups that surround it. Both the bonding electrons and the lone pairs affect the structure of the molecule. The four main concepts behind the VESPR theory are the electron group concept, and this is that it consists of either a bonding group or a lone pair, and the bonding group can be a single bond, a double bond, or a triple bond. There's a bonding pair, which is a pair of electrons that's shared between the central atom and one other atom through a single, double, or triple bond. A lone pair is a pair of electrons that's only connected to the central atom, and these take up more space than a bonding pair of electrons. And the bond angle, which is the angle between the atoms that are surrounding the central atom. So the steps to determine this electron geometry, the first step is that you have to identify the central atom of the molecule. If the Lewis structure is not already provided, you must draw it. So you draw the molecule and you include the bonding pairs and the lone pairs. And based on the bonding pairs and the lone pairs, you determine the geometry of the molecule.
Okay, so the first thing we're going to talk about is electron geometries. And we're going to talk about the 5 basic types of these electron geometries. And there are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And we've come up with the mnemonics so we can remember these. It's linny, tries, playing, table tennis before others. And as you can see, every first letter corresponds to the first letter of one of the electron geometries, so that might jog your memory, help you remember what types of electron geometries there are. Okay, so first we're going to talk about linear electron geometry. And with linear geometry, you have one central atom and then 2 electron groups that go off to the side. So we're going to do a little example to show you how you can come up with this, okay? So we're going to look at carbon dioxide. So we have C, carbon, which is our central atom, that's double bonded to an oxygen on one side and an oxygen on the other side. And forgive me, that doesn't really look like an O, but it's hard to draw on this computer. Okay, so both the oxygens have these 2 sets of electrons that are free, and that's what we would consider our lone pairs. Okay. But they're not on the central atom, so they're not considered an electron group. So you can see there is an electron group here, and here, and that gives us our linear geometry, which has a bond angle here of 180 degrees. So next we're going to move on to our trigonal planar electron geometry. And with trigonal planar, our central atom has 3 electron groups, so circle them here. We have one here, here, and here. And our bond angle here is 120 degrees. Now we have our tetrahedral electron geometry, and we can see that we have 4 electron groups, one here, one here, one here, and one here. And our bond angle between these is going to be 109.5 degrees. Okay, now we have our trigonal bipyramidal electron geometry. And we can see that around the central atom we have 5 electron groups. Here, 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 and one here. And here we have 2 different bond angles. We have the bond angle from the equatorial bond angle, which is here, and that's going to be 120 degrees, and then we have these, which are 90 degrees with the axis. Okay, we have our octahedral electron geometry, which is our final one that we are going to talk about. And you see we have one here, one group here, 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 and here. And our bond angle here is going to be 90 degrees.
All right, so now we're moving on to the molecular geometry, which is when it starts to get a little bit more complicated because we have to start to compare the bonding groups and the lone pair groups within the electron group ideas. So we actually have more types of geometries in molecular geometry. There's still the basic ones that we talked about before, the linear, the trigonal planar, but we also have some additional ones like bent and seesaw or T-shaped. So the first kind we're going to talk about, you've actually already talked about when you were talking about linear geometry, and this is linear molecular geometry. So actually this example is the same exact thing. When our electron groups equal our bonding groups, then the molecular geometry will be the same thing as the electron geometry. The next one is trigonal planar, same idea again. Because our electron groups equal our bonding groups, it's the same electron geometry. We also have the same bond angles. You don't even have to remember those. And this is where it starts to get more complicated when we have a lone pair in the mix as well. So now before when we had just trigonal planar, the electron geometry is trigonal planar, we had an additional bonding group here. But now this is where our lone pair is going to be. But it still is taking up space. It's still repelling the other electron groups. And because a lone pair is actually stronger, it's more repellent than these two guys right here, this guy here and this guy here, they're getting pushed towards each other because this is so strong, it's repelling them and they're getting closer. So our bond angle right here is actually going to be less than 120 degrees. And because this is a lone pair and we have 2 bonding groups and 1 lone pair instead of 3 bonding groups, it has a new name and we call it bent. So tetrahedral geometry, this is the same thing as before. Bonding groups and electron groups are equal, so it's just called tetrahedral molecular geometry. Trigonal bipyramidal molecular geometry is the tetrahedral electron geometry with 1 lone pair. So we would have, like before, when we would have had another bonding group, we have a lone pair about right here. It's going upwards. And same idea again, it's going to be more repellent than these other bonding groups, so they're getting pushed towards each other, and therefore these angles down here and down here, those are all going to be less than 109.5 degrees, and therefore the ones here are going to be greater than 109.5 degrees. Okay, so something interesting about molecular geometry is that we can have the same molecular geometry but a different number of electron groups. So before, when we were looking at the bent molecular geometry, we only had 3 electron groups and we had 1 lone pair. And here we actually have 4 electron groups, but we have 2 lone pairs. So we end up with the same number of bonding groups, and that's what makes them similar. So we have a lone pair here, and we have a lone pair here. And once again, because of their strength, these are being pushed together, and our bond angle is less than Molecular geometry, once again, same thing as the electron geometry because our electron groups equal our bonding groups. The seesaw molecular geometry is the trigonal bipyramidal electron geometry with one lone pair. So we would have had an additional lone pair that would be right here. But it's kind of pushing everything out of the way and creating this seesaw. Fun name, right? So that our bond angles are a little bit less than before. So our angles here are going to be less than 120 degrees, and the angle from this guy to this guy and this guy to this guy, those are going to be less than 90 degrees. And T-shape. So this is also based on the trigonal bipyramidal electron geometry, but because we have two lone pairs, I'll draw them on for you guys. About right here, and another one about right here. Kind of ugly. We have a T shape. So the fun thing about this is that these are actually less than 90 degrees because these are so strong, they're pushing these two down towards this one. And back to the linear molecular geometry. So kind of the same thing I talked about with the bent is as long as we have the same number of bonding groups, we can, we can have the same molecular geometry. So because there's 3 lone pairs and 2 bonding groups. So in this scenario, we would have another lone pair here, one here, and probably one here. But they all cancel each other out because they're pushing against each other, which means that our bond angle is just going to stay 180 degrees. So octahedral molecular geometry, you guys already know about this, same as the electron because the electron groups are equal to the bonding groups. Square pyramidal is going to be when we have a lone pair on our octahedral. It would have been down here. If you guys haven't started to catch on, these names are pretty self-explanatory. This would make a square pyramid, so therefore it's square pyramidal. Square planar, this is when we have 2 lone pairs missing from our octahedral. So they would be here and they would be here. And they also cancel each other out, so that's kind of nice because we know this is for sure a 90-degree angle right there. So I know this is a lot of information to absorb at once, but if you start to get the pattern, start to get the idea of what's going on, then you can figure it out just from basic information. You can figure it out from someone saying, okay, so our electron groups, we have 2, but there's 2 bonding pairs, so we know it's linear. Or our electron groups, we have 4, and there's 2 lone pairs, so we know it's bent. So charts like this kind of help you understand and get the idea and get a visual picture of what each means. But keep in mind that everything does have both an electron geometry and a molecular geometry. They could be the same thing or they could be different things. So this is the other part, just the rest of the chart that you would be able to use to help yourself.
Okay, now let's take a look at a few examples, and first we'll determine the geometry of SO2. Now, SO2, the central atom will be sulfur, and it has 6 valence electrons, and it will be bonded to 2 oxygens. Now, when you're talking about Lewis structures, SO2 does have resonance structure, but when we are trying to determine the molecular geometry, we don't need to worry about that. So we'll just draw one of the 2 resonance structures for now. And sulfur will have 3 electron groups, which would make the electron geometry trigonal planar, but one of these 3 electron groups is a lone pair. So then when you're talking about molecular geometry, the correct answer is bent. Okay. Another example is CH4, and in this one, carbon will be the central atom. And carbon has 4 valence electrons, so it will form a single bond with all of the hydrogen atoms around it.
So we just had Trey on here, who
And in this case, all 4 of the electron groups around carbon are bonding groups. So the electron geometry and the molecular geometry will be the same. So both of them in this case are tetrahedral. One last example we can look at is SF6. And again, sulfur will be the central atom and has 6 valence electrons. So because of that, it will form a single bond with all 6 fluorine atoms around it. And all 6 of the fluorine atoms also have 6 electrons, or 3 lone pairs, but we're not going to worry about drawing all of those since we only need to focus on the central atom. And in this case, sulfur is forming 6 single bonds, so it has 6 electron groups, all of which are also bonding groups, so the electron and molecular geometry will be octahedral. And now for some practice questions. What is the electron geometry of a molecule with 6 electron groups, 4 bonding groups, and 2 lone pairs? Now, always pay attention to the wording of a question because this is only asking for the electron geometry. So you don't even need the last 2 pieces of information that it gives to you. All you need to focus on is that it has 6 electron groups, and because of this, the correct answer is octahedral. Now, instead of electron geometry, answer the question, what is the molecular geometry of a molecule with 6 electron groups, 4 bonding groups, and 2 lone pairs? And for this, you need to take a look at all of the information provided. And because it has 6 electron groups, but 2 lone pairs, the correct answer is square planar. Okay, now determine both the electron and molecular geometries of PCl3. Now PCl3 will have 4 electron groups. 1 will be a lone pair and the other 3 are bonding groups. So in this case, the electron geometry and molecular geometry are different. And so the electron geometry is tetrahedral, but the molecular geometry would be trigonal pyramidal. And one last question. Determine both the electron and molecular geometries of H2O. Now, H2O should be a Lewis structure that we're all familiar with by now. It has oxygen as the central atom, bonded to 2 hydrogens with single bonds, and then there are 2 lone pairs on oxygen as well. So total there are 4 electron groups, but 2 of them are bonding and 2 are lone pairs, which will lead to an electron geometry that's tetrahedral, but a molecular geometry that's bent.
So as always, there are some exceptions to the rules. One major point to keep in mind is that if a double or triple bond is used, as opposed to a single bond, more space will be taken up because more bonds will be present. But sometimes the VESPR theory simply fails, like with the isoelectronic species, which are molecules that share the same number of electrons. According to the VESPR model, the shape of a molecule is determined by the number of valence electrons, including the bond pairs and the lone pairs. But with 2 different isoelectronic species and them having different geometries, they can still have the same number of electrons, and this proves that the isoelectronic species don't follow the VESPR theory. So a perfect example is one with IF7 and TEF7 with a 1- charge. Both of these species have 56 valence electrons, so the predicted VESPR geometry for these 2 species would be pentagonal bipyramidal. But this is incorrect because the VESPR theory does not take into account other external factors that may alter the shape of the molecule, including electron diffraction. The VESPR theory also fails when predicting the structure of transition metal compounds because some may have stereochemically inactive electron pairs, which may cause the valence shell s electrons in these elements to exhibit non-bonding behavior. Transition metals have a tendency to have high atomic masses, and this causes the stereochemically inactive electron pairs. And so there's going to be an example on the next slide explaining this in more detail. So here's a little reminder for you guys, just in case you forget, that transition metals do not go with the VESPR theory. And as I said before, here's a little example explaining why transition metals don't follow VESPR. So you can see with this lovely image that TeCl
Cl6 with a -2 charge. Here's the drawing of it, and it does not follow VESPR because the VESPR theory would predict that it is pentagonal bipyramidal, but it turns out that it's actually octahedral. And so while we don't need to know pentagonal bipyramidal, I just thought it would be a good example to show you that most transition metals don't follow the VESPR theory.
So here's a little practice question. What are the approximate bond angles of the molecule CH2O? So as you can see, the oxygen has a double bond, meaning that it's going to be more repellent than the single bonds on the hydrogen atoms. This means that there will be 2 greater than 120 degree angles, and there will be 1 less than 120 degree angle, the one between the hydrogen atoms. So we can see the VESPR theory in everyday life when you think about how people stand in an elevator. When people first get on the elevator, they try and stand as far away as possible, and this trend continues, just like electrons, how they try and force themselves as far away from each other as possible. You can also see the VESPR theory with puppies eating from the same bowl when they all have angles between their bodies. And here are works cited if you're interested.